Shall we start? Okay, so there's a lot to do today. No, it's the last lecture on loops. There's something I have to do that is cover the vertex amplitude. How do you get it? How do you define the quantity that Pietro was computing, the one that Carlo was describing? So you have three parts. One where I tell you about principles. Then I'm going to cover some of the mathematics that are already introduced. And then we go back to this central object that tells you how to put one of these quantum of space, one of these quantum polyhedra, and you put them in space-time. Okay? You have the notes. You know how it works. Download them. Don't copy. Ask questions. Okay? So let's see. I think a way to start and present this story is to tell you about the gamma puzzle. If you haven't heard about the gamma puzzle is the following statement. We looked at spin networks. No? We know the states that are labeled by a graph, spins and intertwiners. We know how they describe the geometry of space. We learned about fluxes and how they essentially proportional to angular momenta. They have the same properties of angular momenta, but these measure areas, so they should be something with dimensions of area. G h bar gamma. We saw that the area gap, for instance, depends on G h bar gamma. The spectrum of any geometric observable depends on the right power of G h bar gamma. Okay? Where gamma is the Barberi-Mirzi parameter. On the other side, when we define the dynamics is the transition amplitude from an initial state to a final state. This is the thing that we have to discuss, and you can formally think of it as a path integral over geometries weighted with the gravitational action. And the gravitational action over h bar contains here gh bar, the curvature scale, the Planck curvature scale. So you have these two objects, the area gap scale and the Planck curvature scale. One is gh bar gamma and one is gh bar. And in all perturbative phenomena that you can obtain from this semi-classical picture, where you trust this formal quantity by saying, well, let's assume that there's some classical space-time and then perturbations. Let's look at the dynamics of perturbations. They're going to depend on gh bar. You're going to see examples. I mentioned one example of something of that kind. You can look at primordial curvature perturbations. They remain imprinted into the anisotropies in temperature of the CMB. The amplitude, that power spectrum, contains a gh bar. Okay? Gh bar, Hubble squared at the end of inflation, divided by this lower parameter. But in quantum geometry, the only quantity that you have is gh bar gamma. How can you possibly obtain perturbative physics that we trust? And in fact, we have already measured some of it out of a theory that contains only the combination gh bar gamma. As you see, the way I'm phrasing the problem doesn't rely on knowing all the details of how all these things are formulated. It's this theory style of find the dimensionful quantities, identify what your predictions can depend on. If this is the only combination, then how does gamma disappear in the perturbative regime? Do you see the puzzle? Do you have an idea, a proposal, a comment on solutions? Hands. I want hands. Think about it.
I mean, I don't really have a solution, but I just remember that when you were talking about like the conjugate momentum structure, what you did was like pull 1 over gamma in front. Mm-hmm. So you had 1 over gh bar gamma in front. Mm-hmm. And then the variable we were looking at was basically like gamma times that. So maybe, I don't know. Yeah, that's the starting point. I don't know where to come from there.
Good. So this was one point. Like, how did we get this GH bar gamma? We wanted the connection conjugated to the flux, but to get a connection, we needed a gamma. And we paid a gamma, and this was how we produced this. And all this, you can think of it as robust in the sense that it doesn't depend on the details of this action. It really depends on the physical ingredient, the physical statement that fundamental degrees of freedom are holonomous and fluxes. Okay, so in that sense, it's robust. It's more robust than saying this is the action. We are not quantizing general relativity. We're identifying within general relativity what are the fundamental degrees of freedom. These conical curvature, conical defects, or these loops that encircle curvature. So that is robust. That is, when somebody was asking Carlo, what is the thing that we think is really robust that characterizes the theory? Well, it's all these geometric structures, quantum geometries with discrete spectra, and they all depend on this. But then the puzzle remains, and the puzzle was there. I don't think that we ever sharply tracked it to this, but many of us around between 2005 and 2008 were thinking about this, like, how do we get gravitons? How do we get perturbative quantum gravity? All that is GH bar. How do you get GH bar physics out of something contains always this constant? Do we have to fix gamma to, I don't know, 1 or 1.2? Does the theory make sense only for some values? Or 0.2? I don't know. More comments?
I mean, couldn't be... Do you want the microphone?
Go.
I mean, couldn't be just running? It's like asymptotic
Good.
freedom.
It could be running. It could be like it goes to some special value. But then if you remember how we got it, this was a topological term, the coupling to a topological term. And so local 3-level and 1-loop things cannot change the coupling to something topological. It has to be something global. And Simone actually looked at the perturbative expansion, and you expected it doesn't run. You do order by order. You find something, and something else that cancels it, and it doesn't run, as one could guess, but it's good to check explicitly. Other ideas? Okay, 1, 2, 3.
Kind of coarse graining or averaging.
Coarse graining or averaging?
Well, when you look at the black hole entropy, you only get GH and
Sure.
no gamma, so
There might be some relationship of whether or not the GH bar gamma would only appear in types of, excuse me, like kinematical computations compared to when you're considering the dynamics.
Good. So let's separate questions or physics problems where we expect one and where we expect the other. So you're saying, well, it looks like black hole entropy, area of a 4GH bar. That depends on this one and not on this one. I was saying before, primordial power spectrum, there can be genuine loop corrections, but to get the big part of it, the one that is already measured, you don't need loop corrections. It's perturbative quantum gravity. Can you name something that we expect to depend on GH bar gamma? It would have to be a measurement really of area, for instance. And somebody was asking me, like, wait, but area, don't you have to do length times length? How do you get area if you don't have length first? And there is this idea of, like, what if something measures directly area? Do a cross-section, do a scattering electron-positron, and look at what shadow one sees of the other. That's the cross-section as units of area. It's measured in area units in barn. If you go to high energy, it's smaller, like picobarn. And if you were able to resolve the spectrum, the prediction is that you find one of the eigenvalues in this spectrum. But that remains the puzzle. Like, that would be something that depends on GH bar gamma. And there's other physics that depends on GH bar. So gamma, yes?
In the area, you have GH bar gamma times square root of j plus 1 times j. So in the semi-classical limit, you take the limit of large j's. So maybe you don't just take like j going to infinity, but like gamma times j going to infinity, and that's the classical limit that you should take?
It's a good point. It's a good point. Like, what do we interpret semi-classically? Do we interpret it like, is it j large? Is it gamma j large? It's a good point, and it identifies this thing of What are the observable? What are you holding fixed? Okay. But it's clear that we need one more ingredient. We cannot do it with one more ingredient. We need somewhere gamma independently. And this is all the story of this vertex. This introduces independently gamma. This, does it work? Pop. Yes. This is the Engel, Pereira, Levin, Rovelli 2008 model that contains this map Y gamma. It has a gamma, it contains only gamma. So what I have to do is to tell you how gamma enters. And Carlo answered it. It's somewhere here. There's this P equal gamma J. That's what I have to do. But keep track of gamma everywhere because this is the piece that we need. Okay? Go ahead.
Should you give it back?
You cannot leave. Okay, so what I'm gonna do is to split the presentation of the vertex. So first, focus on an elementary transition, for instance, from 1 to 4, for one tetrahedron to 4, this 1-4 move that Tetera was telling us about, in terms of a form that has one edge that goes into 4 edges, and then each one of them, the link spans a phase. It's easier to draw and keep track of things by just drawing, if you want, the tetrahedron is a point, it evolves in time, and this is like the word line of the tetrahedron. And then there's this branching, 1 to 4. And so often I'm going to just draw it this way. It's faster, it's easier. I'm putting arrows, 1 in the past, 4 in the future, 1, 4. And then we have to ask all the questions of, is 1, 4 equal to 4 to 1, to 2 to 3? For the moment, I'm just going to focus on this one. And we have to give this transition amplitude. The theory is, the dynamics of the theory is defined by this transition amplitude. And one can give arguments starting from classical general relativity or how a quantization captures these degrees of freedom gives you a proposal or a definition. I'm going to take the reverse point of view of let's postulate something that is just group theoretical, just putting together invariants of the Lorentz group so that then that gives a dynamics to these transitions that captures gravitational physics. And so I have to address the thing of I need to get GH bar somewhere. Okay? So here's the list of principles, the way I understand them as if you want to build a spin-foam vertex, you need to satisfy these principles. We want a spin-foam vertex for quantum gravity, so there's going to be one more point. We want quantum gravity. We don't want a topological theory. We don't want any theory, spin-foam theory. We want a spin-foam theory for quantum gravity. First, degrees of freedom. This we have discussed at length. You can think of them as these nodes. These elementary degrees of freedom are spin network nodes. You can think of them as quantum polyhedra or as SU2 intertwiners. So there's this object mathematically that I'm going to refer to all the time that is this SU2 invariant tensor. Each one of them is a quantum polyhedron. And so we want a map from one intertwiner to 4 intertwiners. Okay? Now, intertwiners are for the rotation group of symmetries of space, of a patch of space. There's a question I've been asked many times in the last week of, yes, but we want to do space-time. Why are you telling us about space first? How does this fit in space-time? Okay? So there are always the two directions. So you have space, how do you embed it in space-time? And the other one, you start from space-time, how do you project down to space? And the theory has to be invariant under space-time transformations. So a way of going from space to space-time is I first build this quantum of space, then I tell how this sets a frame, like a massive particle sets a frame, the frame of the rest of the particle. A tetrahedron sets a frame in the sense of in 4D space, there's a plane, a space-like plane that contains the tetrahedron. Or it's easier to say by saying that there's a 4 normal that is time-like. Okay? And when I speak about Lorentz covariance, I wanted my embedding of quanta of space in space-time transforms covariantly if I boost this tetrahedron. I have to be able to speak about boosts of the tetrahedron. It's invariant under rotations in space because the normals sum to 0, but it's not invariant under boosts. No, it's like a massive particle. A massive particle has a 4 momentum. The 4 momentum is not invariant. You can ask questions about the particle that are Lorentz invariant. For instance, for a massive particle, you can think of them as a finite dimensional representation of the Poincare group. Poincare, you have P mu and J mu nu, and the mass is 1 of the Casimir, P mu squared is minus m squared, and this is invariant. Okay? And then if you want to speak about spin, spin is something in space. So how do you think about spin in space-time? One can say, well, go to the rest frame of the particle, and now you have just space. You speak about spin as you already learned in non-relativistic quantum mechanics. But if you want to speak covariantly, don't work with 3 vectors, work with 4 vectors. And the object is the Pauli-Lyubaski 4 vector that measures the spin of the particle in a covariant way. And if you check, if you choose the, sometimes people say the coordinates or the gauge where this one is 1, 0, 0, 0, or P mu is 1, 0, 0, 0, then you go back to space. But you don't have to. This is covariance. And the last step, you want that these objects interact in a local way, that is the transition from 1 to 4 depends only on something that is at the intersection, at the vertex, not somewhere else. It's not non-local, it is local. You want it to be, you require it for calling it a spin form. That it's local, that gives you this change in number of excitations, and you want it to be causal, it has to know the causal structure of what goes into what, and most importantly, you want it to be Lorentz invariant. Okay? So here, when I require Lorentz invariance, it means that I need all the tools for speaking about these tensors, like the intertwiners, but not for SU2, not for rotations, but for the Lorentz group. And so what I'm going to do is to go back, do a little bit of mathematics, and then we go back to the physics. Okay? And this is a place where I should check questions on the logic. Yes, Gori.
It's about the last point you mentioned, that the physics is local in the quantum theory, but we know, for example, Carlo mentioned in the last lecture that one of the successes of the theory is that the vertex amplitude has the form of e to the I Regge action in the large spin limit. Mm-hmm. And we know that Regge calculus is not local in the sense that the sum involves a lot of geometric relationships between the edge lengths that span the triangulation arbitrarily depending on how the graph is. So how do you link the quantum theory, which is local, to a classical theory which is not really local, even though we clearly see that the vertex amplitude gives you that connection, but the physics is not really the same?
Good. I think I understand the question. Let me add the word in the list. There's local, there's non-local. Let's use also ultra-local, that is even more than local, okay, so that I have three places where to place things. So when you do field theory, you have derivatives. The Lagrangian, the action contains 2 derivatives, and then you can go on and say there are corrections that have 4 derivatives and so on. And so those they are the same as saying you have a function, you can expand it at a point, and there's the value of the function at a point, and then there's the first few Taylor approximations that you characterize in terms of derivatives. And then if you want to know something very far, you need many derivatives, and so it becomes a no-local notion captured locally. But the lowest order term has only few derivatives, 2. And so this is what people generally call local, like first neighbors. If it was on a lattice, This would be first neighbor coupling and not coupling with everything arbitrarily far. Okay? Now you're saying Regge calculus. Well, it has something of locality, that is the action is the sum of local terms, like 4 simplex by 4 simplex. But then it's fair to ask, like, how can there be things that propagate? There has to be a coupling between this one and this other one. And so these are these gluing conditions. This piece and this piece, they have to match on the boundary. And so here there's something very similar. There's a matching on the boundary. The volume coming from this side is equal to the volume coming from the other side. And you can think of the vertex as the first neighbors interacting. So there is no locality in the sense of this vertex knows about vertices far away. And it's a theory with finitely many degrees of freedom on this complex. And so the theory, the effective theory with derivatives is to be understood as an effective theory, as when you go from a lattice to the effective theory where you Taylor expand everything. Okay. Yes.
Yes, so my my question is what we mean by causality. Yes, because previous question was what we mean by locality, so I want to ask what we mean by causality.
Good. Yeah. So at this level, I only mean causal relations, like this is future pointing, this is future pointing, this is also future pointing. They interact at this vertex. From this to this, you can boost. From this to this, there's no boost that sends one into the other. You can do first a time reversal and then a boost. So if you want, it's a causal relation between given a region with a boundary, can we tell what degrees of freedom are on this side of the boundary and what are on this side? That's all I'm using as causality. So it's a microscopic causality. And then one has to ask all the other questions, like how do you get light cones globally or causal structures globally? It's a way more local notion at the level of the single vertex. That's what I'm referring to.
So this causality is basically encoded in the fact that we cannot do Lorentz boost from the future to the past.
Yes.
Okay.
I have a follow-up question. So so these edges all have arrows, and in Pietro talked about that a lot, right? And about the graph, and then said, so you have to choose some kind of arrows, but it doesn't really matter what you choose. You just have to make a choice and stick with it, and the calculation will be the same. But that was like for the spatial spin foams, spin networks. So this is a spin foam now, and here it seems like the arrows do have a meaning in the sense of they determine which is the in state and which is the out state, kind of. So is that something you have to put in extra, or is that somehow encoded in the vertex amplitude?
Yes, I'm going to address this at the end. Okay. So there's a question of what is the boundary state? Does the boundary state knows about the causal structure? Well, it knows about the boundary causal structure, the fact that these are two space-like connected in this way, so encoded in the boundary. And then the quantum theory gives you the transition amplitude, that is the sum of geometries compatible with this boundary. And so there, when you tell what is the vertex, you have to decide what is your theory of quantum gravity. Is it a theory of quantum gravity with fixed causal structure, where you have first decided these are the causal relations, so now it's sum only over geometries at fixed causal structure, or do you sum also over causal structures? Okay, so the vertex as has been defined, and as I'm going to first present it, is with also the sum of causal structures. It cannot tell which one is past and which one is future. There's an average between the two. This is e to the is complex plus complex conjugate. And you know, once you have that, it's fair to ask, like, can I think of it as the average over two? What are those two? Can I do the decomposition? And we have worked with Chao Song over there. Do ask Chao Song, and I have a slide at the very end. Okay? Let's go ahead. Yeah? So now we are motivated. Now we have to do this. We have to go through these representations. So there are books, there's literature, older, newer. This is a topic that was essentially developed in the 60s as mathematical physics work. There is an introduction by Pierre Martin Dosseau that is of the style that I like, that is there's just the minimum to get up to the end and you get everything, and everything is explained step by step in this same logic that Ethera was following of check out what acts on polynomials, write everything in terms of polynomials, in terms of functions of z and z bar, and look at how you define first SU2 in that way, and then the Lorentz group. Okay? So I recommend looking at that. And I do have a warning, like most physics textbooks tell you about the Lorentz group, but they really tell you only about finite dimensional representations, like vector, tensor. Those representations are not unitary, clearly, because this is the Lorentz group. It's not a unitary group. We're interested in unitary representations because we want to do states and unitary transformations. So I really need unitary transformations. And that's the difficult part. SO13 is non-compact. The unitary irreducible representations are going to be infinite dimensional. And we do have to go through that to understand them. So that's my short introduction to exactly this topic. And then I'm going to give you an analogy or an example, or two examples maybe. So we start with something familiar, that is, you can think of the generators of Lorentz transformations as objects, 4x4 matrices that have these commutation relations. If they don't look familiar in this way, it's because probably you learned them not in a manifestly covariant way, but in a way that is split into rotations in space and boosts. To do that, you do have to choose some reference time-like vector to say what are rotations, rotations in what frame. And you can think of it as a, a gauge fixing or a choice of coordinates, or if you go back and think about the relativistic particle, this is physics, this is the form momentum of the particle. Once you have the form momentum, your preferred frame for a massive particle, and then you can decompose everything into the rotation component and the boost component. And the rotation component is purely space-like, the boost component is purely space-like, and so one writes it in this way. Let's check that I put the signs correct. Rotation with rotation gives rotation. We did it. Go back, it's a rotation. Rotation with boost, it rotates the boost, so plus sign. And then this one is the one that makes the group non-compact. If you boost in one direction, and then you boost in another direction, then you boost back, you don't come back non-rotated, you come back rotated. And there's a minus sign here. This minus sign is what makes it non-compact. This minus sign is what makes this what we call boosts. Okay? So all this is what we need before doing these unitary representations. These are just this is the algebra that we want to represent on a Hilbert space. There's one more ingredient that is useful to have, that is, how do you write things that are invariant under rotations? How do we write Casimirs? Yes?
Sorry, can you briefly explain again how this... can you briefly explain again how this minus sign makes it non-compact? Or is this like intricate detail?
Yeah, it's not immediate. It's a way to track it. That's where you see it, but there is a calculation to do to see it. Yeah, because this is at the level of the algebra. Okay, so that's an exercise that we can work out together. But in general, that's the symptom of the non-compactness. Good. So Casimirs, it's clear that this one is Lorentz invariant. All the indices are contracted. I didn't use anything external. This one is Lorentz invariant. I only used the epsilon, transforms as a tensor. When I split them into boost and rotation, it's clear that they are rotational invariant. Is it clear that they are also Lorentz invariant? Well, now Lorentz invariance is not manifest, so you really have to go and check. But maybe you recognize them. This really looks like the Lagrangian of the electromagnetic field, E squared minus b squared that is Lorentz invariant. In this one, I don't know if you thought about that, but it's another invariant thing that you can write. Electric dot magnetic that is invariant. Okay, so as for L squared, that has spectrum j times j plus 1 for SU2, these ones have spectrum, they have eigenvalues that are labeled by two quantum numbers. We have two Casimirs. One is continuous, and one is discrete half integer. And so if you want to expand a function, it's not a sum of spins, but now it's a sum of k and integral over p continuous. If you want, okay? So this is the Hilbert space that carries unitary representations of that group that's split in irreducibles. Now, rotation group is a subgroup of the Lorentz group. It's not canonical. You still always have to give me some additional reference. But as it's a subgroup, every representation of Lorentz is also a representation of rotation. Nobody guarantees that it's irreducible. In fact, it is irreducible. That means if I take an irreducible, it's going to decompose as a sum of SO3 representations. And the calculation that is hard, that's where you really need all the machinery, is check the degeneracies, check where it starts. The lowest weight, the lowest, there's a mistake, this is J. The lowest J is J equal to K. This is going to be important, no? If you think about rotations, it's Jm, and m starts at minus j. That's the minimum. That's the lowest weight. And the highest weight is plus j. And here, it's unbounded. It's non-compact. There is no maximum. There's no highest weight, but there is a lowest weight. OK? And you start from k. And as I'm there now, you can say now that we have all the things that are a set of compatible observables, you can say instead of doing Jm, I do the Casimirs, and what is left to split the degeneracies. So I diagonalize one Casimir, and I get this. I diagonalize the other Casimir, and I get this. And then these two we know, J times J plus 1, and M. So in that way, you learn what are the labels here inside. Jm you're familiar with. You also need this pk. That's why this list is so long, the list that enters the definition of the vertex. Comments? Yes. Cube.
There was a writing that we have a principal series. So what are representation outside this principal series?
Yes, good. Yeah, so that's correct. I'm telling you about unitaries, but I'm telling you only about the principal series. It's the only one that is relevant here. The reason why it's the only one that is relevant here is that if you start from functions of group elements and you ask how can I expand a function of a group element in the same way as you do a function on the sphere expanded in spherical harmonics, it turns out that these are the only unitary representations that appear. Let me say this once more. Take a function on the real line. We all learn a Fourier transform, that you can write that function as an integral over contributions e to the I kx. So function on the real line, the symmetry group is translations, R. And what one is doing is representation theory of that. And the basis is e to the I k. And the coefficient, the Fourier transform, they are the coefficients of that expansion. So harmonic analysis for translations is Fourier transform. Harmonic analysis for rotations is spherical harmonics. Jm, sum over Jm with coefficients. And so now one can ask again, I want to do harmonic analysis for functions on the Lorentz group. I want to do the analog of the Fourier transform. As Etera was calling it, I want the Peter-Weil theorem. And this is what you need. It doesn't mean there are also other things, but I'm taking this path of, I'm going to cut all the things that we don't need immediately, and they are there, and they are in this big book where either rule or other books that you might like on harmonic analysis. Okay?
Okay, so the claim is that only principal series is needed to do Peter-Weil theorem on SL2C.
That's correct.
Okay, and are those representations some kind of analytic continuation of SU2 representations, or is it wrong to think
That is
that
correct.
way?
It's very difficult to. It's very difficult. Once you see the trick, it's not difficult. But keeping track of all the terms, it's non-trivial at all. To the point that there's a paper of 3 or 4 years ago by Pietro where he figured out how this is done. But it is true. It's a fact that you can start from Euclidean group and then find the correct analytical continuation to these ones. And you get only the principal series. That's the important thing. So it's a way of understanding the principal series. Okay, there's a question that I have for you now. Have you ever seen this? When I mean have you ever seen it, I mean have you ever seen it in any other physics class that is not loop quantum gravity? Do you need this just to do loop quantum gravity? Or like maybe I'm a mathematician who does harmonic analysis on various groups and Lorentz group is in my list.
Parts of it are in like Weinberg's chapter 2.
Yeah, I think quantum field theory, of course.
Okay, so if you go through there, you find something that it's surprisingly much easier than what I explained, because instead of doing unitary representations of Lorentz, it's doing unitary representations of Poincaré. And by adding p mu, makes everything much easier because you can say I first diagonalize mass, and then I go to the little group, and I just have to say if it's space-like. So I really just need to know rotations. Unless the particle is massless, then I need to work a bit harder for finding the little group. But here we are not free to choose the little group because we don't have a canonical Ni. This one is dynamical. And so that's why I was asking the question. Most likely you have seen unitary representations, but not for Lorentz, for Poincaré. You've seen them for rotations and for something else, but not for this thing. Unless you have seen it somewhere else, so that's why I'm checking. Have you seen this somewhere? Because I'm going through examples now. How can you give you examples if there are no examples?
It kind of looks like just quantum mechanics.
Good. It looks like quantum mechanics. I'm doing quantum mechanics. When I say JM, everybody has in mind, like you do the quantum mechanics of a particle on a sphere, it's going to be JM. I do the hydrogen atom, I get the spherical harmonics. So is there some quantum mechanical system where this is important? Like, why Fourier transform is so important? Because there are lots of Hamiltonians that are translationally invariant. So if you want to do the spectrum, Fourier transform helps. Why SU2 is so important? There are Hamiltonians that are invariant under rotations. So I need an Hamiltonian that is invariant under Lorentz transformations so that then the spectrum is this one, and then I have a physical intuition for where all these mathematical relations come from. I'm sure that you have seen one. So I'm promising examples. I have two. I'm sure that you have seen one. One is for SO4, the hydrogen atom, or the particle in a Coulomb potential, has the SO4 invariance. It's not just invariant under rotations. There's, if it's an ellipse, there's a special direction, the axis of the ellipse, that is preserved. This thing doesn't precess. And so that quantity, that's the length vector. If you check the algebra, this is really the algebra of SO4. So the hydrogen atom is SO4 invariant. That's how Pauli found the spectrum of the hydrogen atom. He didn't solve any differential equation. He was like, I know representation theory. I've studied this. Can find the spectrum. Here we need the non-compact version. The non-compact version is, don't look at bound states. Look at scattering states. You have a Coulomb potential. You shoot a particle. The particle is deflected. You get this hyperbolic encounter, and there's still a preferred direction. L is the plane of angular momentum. And the other, this is still the length vector. And if you check, just because it's unbound motion, you find that the angular momentum and the length vector satisfy exactly the same algebra as for the Lorentz group. They commute with the Hamiltonian, and so if you want scattering states, For a free particle, scattering states are just plain waves, so they are labeled by one representation of the translation group. But for scattering states, they have to be labeled by representations unitary of the Lorentz group, with a P and a K, which P... Say it again?
Is that what Tolman was doing?
Yes, I learned it from there. Yeah. So if you... Toller was Carlos' advisor as a kid. My grandpa. Yeah. You can check L dot K is clearly orthogonal, so it has to be 0, so either P or K is 0, but the energy is not 0, or not infinity, so the representation is K equals 0, P equal 1 over square root of M. What is alpha? 1 over 137. Now we are doing hydrogenatomy. Okay, so that's the example. If you want to solve scattering, long differential equation calculation, if you're given it as an exercise, unless you know a bit more mathematics. It's like, you have one more tool, you can use it. So pk 1 over square root of energy 0 is scattering. The claim is gravity is P equal gamma j, K equal j. Now you see that you have a gamma. That's what I was promising. You need somewhere a gamma alone. If you don't have a gamma alone, but always multiplied by GH bar, you cannot get perturbative physics that we're familiar with. That's the place where this map, Y gamma, that tells you how a plane in space, you can think of it in space-time, because there's a frame of the tetrahedron, or the chunk of space of which this plane is part of. So you have two vectors, the 3 vector and the 4 normal, that gives you 2 form, or a space-time plane. And the quantization of that is this object. I haven't told you yet why exactly this one. I have only an equation here, an equation that relates the two Casimirs. If this is the condition, then there are two solutions, these two. If you also require P to be positive, this is the only one, and that's what we use. Okay? And that covers all the mathematics that I was promising I would cover before going back and telling you about the vertex. I think I should give you an opportunity to ask about the examples. 1, 2.
So the P, what
So what's the physical in the second one in EPRL spin
Yes.
form? So what exactly is P here? Is it like a spin momentum?
Yeah. So when you measure areas, we learn that area is proportional to J, but it has a gamma J always. So if you look at it from a space-time formulation, where you are never broken, you kept manifest all the symmetries, you can really think of P directly as the quantum of area. Okay. And then GH bar, often one just says, oh, I work in natural units, GH bar, G is 1 and H bar is 1. But it's general logic. Once you do that, then you cannot make any of these arguments. That's why I was saying in the very first lecture, we know special relativity. See, I'm going to put it 1. I don't need to track it. But I want to track what's classical gravity, what's quantum gravity. I need to keep track of GH bar. Otherwise, I cannot make checks. And in the same line, there was a question earlier about how do we communicate with other people outside of our community. There's a standard strategy that is the same as when you teach a new class. That is, find what is the common physics that we all know, the hydrogen atom, and compare it to physics that we have in common, because there we have the language in common. And once you have the language in common, then you can build over that thing that you have in common. We all studied the hydrogen atom if we had the undergrad physics training. At least that's what I tried to do. That's why last night I worked out this example together with a few here. There was another comment. Yes.
I just want to ask again about the J+1 versus J.
Yes.
So I think Pietro said, so this J is only like asymptotically if you take J going to infinity, versus the J+1 would be the exact solution to the equation you wrote down, right?
Yes, this is the question. Why why there are two things floating around, which one is which, is it one an approximation, one good. So I think the short answer is that we are defining a theory, and the theory is not free of choices, or you can think of them as different theories once you define them in this way. They are the same semi-classical limit. To tell which one is which, you would have to go to this gap or very low. That doesn't mean that there are no other principles that can fix those ambiguities, but one has to declare them. So this is very similar to the ambiguities when one says take, I'm calling it L, take L square. What's the spectrum? It's J times J plus 1. But if you write L out of these Schwinger oscillators, then you can define directly L squared as I times I plus 1, and the spectrum of I is exactly J. And so it becomes a physical question where there is L squared and where there is I. And so similarly here. And so at various points in the construction of the model, there were groups that were guided by, well, if the semi-classical limit doesn't work, it's the wrong, so it's a zero check. But all of those cannot distinguish the exact representation because it's only large J and they all agree. And then there are impositions of exact equations. So you can ask, for instance, a matrix elements have a property, or you can, so when I say this one, I don't mean it as an approximation. You can take it as an approximation, but I mean it as this is the unique solution of annihilation operator on the state 0, and the person who figured out this way of doing it, that to me is the cleanest, is Wolfgang Wieland. Wolfgang Wieland found a way of writing the constraint K equal gamma L in a way where you say, I write it as an annihilation operator, and all my states have to satisfy annihilation operator on the state 0, and this one is the unique solution. Okay? And clearly, once you're working with operators, maybe you can do, like this, it's this plus 1. Is this natural or is it by hand? If you have an argument, it's natural. If you don't have an argument, then all the difference is, do you put it or do you not put it? Okay? So in the development of the theory, there's still another thing that I can say that is this one. You see there's a lowest weight. So do you choose the lowest weight or lowest weight plus 1? No? Asymptotically, they are the same. So if you have an argument for saying this is the correct thing, then you get 1. Okay?
Yeah.
So it's not an approximation ambiguity. It's one more statement one has to add to say this is the theory. Okay? And in numerical calculations, as Pietro was saying, like I have to make a choice. And I make this choice because numerically this one is the one that I chose. Okay, we go ahead. Part 3. I have to tell you again, you have heard this thing, but it's good to say it once more. Where is this Y gamma map coming from? And a way of thinking about it is the one that I already discussed, that is, there is this topological theory where you can do everything. It's empty, it has no local degree of freedom, but you can quantize it, and it's completely under control. You can unfreeze 1 degree of freedom, and that's what generally people do. They say, take a space-time with non-trivial topology, and then you just have to say what happens when I go around like this torus in space-time, and then it's elementary quantum mechanics. This is well understood. And this is general relativity, is rich, it has infinitely many degrees of freedom, it has perturbatively gravitational waves, non-perturbatively rich classical theory, and the way you can get general relativity out of the topological theory is that general relativity is you require this B field to be of this form. Now note that you can make the statement in a more constructive way by saying, look, I can do some algebra and turn this equation equivalent into this equation. No? Say that this combination of B fields is equal to frame wedge frame. When you look at frame wedge frame, this is a 2-form, but it's a very special kind of 2-form. It's just the wedge product of 2 1-forms. It's what people call a simple 2-form. spans a plane in a very special way. So what you can do is to say the condition is the B field, this combination is such that there exists some one form. And so then you don't have to say the one form that is the frame field. You just have to prove existence, and then you're done. And now in the quantum theory in spin forms, well, we do this controlled construction where you first build a theory with 0 degrees of freedom, 1 degree of freedom, 2 degrees of freedom, and then you build the full Fock space out of them. And so you want to impose the constraint unfreezing a few degrees of freedom, a few conical defects at a time. And to unfreeze a few at a time, you impose the constraint on a 2D phase, on a triangle, and a 2-form naturally integrates on a triangle, and that equation, this one, 2-form, on the frame of the triangle, with the input, the statement that these triangles are space-like, these defects are space-like. This is part of the definition of the theory. They are space-like, they have a time-like normal, so you have to impose this condition that if you write it in components, if you check a few pages earlier, this is what I called boost, and this is what I called rotation generator, angular momentum. So this one is exactly k equal gamma L. This is an exercise to do, especially checking the coefficients. So 1/2 here. This thing is often called the gamma simplicity constraint. It's not the condition that is simple, it's the condition that is gamma simple. Now you have this gamma, and now you can ask, how do I quantize the boost? Well, we learned representations of the Lorentz group. You can do the hard work of saying, well, this is a thing in phase space, and then I put hats turning things into derivatives, but then there are all the ordering ambiguities. How do I fix them? Well, don't break Lorentz invariants by doing that. That's how Pauli solved the hydrogen atom. He didn't get a split between 2s and 2p that you would have got if you had done some approximate calculation with differential equations instead of solving it exactly. He got exactly the degeneracy. The degeneracy comes from Lorentz symmetry for the hydrogen atom. Or there, I should say, SO4 symmetry for the hydrogen atom. So if you do that, here I'm giving you Wolfgang Wieland's version. That is, these are 3, but the commutators don't close, so you don't impose all of them. How do you do that? Well, you extract 1, because there's always the one that points in the direction of the normal. That sets a frame. This one you solve. And then there are the 2 that twist or rotate, or at some point people are calling it gamma flip. They do this gamma twist. And that one, you treat it as an annihilation operator. And if you look at the solution of these 2 equations, there's a unique solution that is, there's a J, that is the surface in space, embedded in space-time with P equal gamma J and K equal J. So 2 things. One is the lowest weight, that is JJ, and then it's gamma simple. Okay? And that was a lot. I think I'm going to let you ask a couple of questions. Corey. Cube.
I think I have the answer to the question, maybe,
Ask.
because of the things on the board, but I'm not sure. That's why I'm
Ask
asking.
away.
The set of states you get from this Y gamma map,
Yes.
do they span the kinematical Hilbert space for one link, so L2 SO13, or do they span a smaller subspace, because you're limiting to
Good.
gamma simple representations?
Good. So this is really, take your spin network in space, and now you just realize that this actually, I can think of it in space-time, and every single thing that we wrote in space for quantum geometry of space, now you can think of them as quantum geometry on a spatial slice of space-time. So the map is just this injection or embedding, okay? Okay, I have one more thing to do to close. I think everything that is in here I already said. If you didn't, so it's an injection, JM goes into something for rotations, goes into something for Lorentz. You can do it for any pk. But here you're doing for this special pK, and these ones know about gravity, okay? They know about gravity in these two ways. It's the lowest weight, and it's gamma simple. So you can say spin foam is take spin networks and embed them lowest weight gamma simple, and you said everything. The analogy is if you have rotations, they are labeled by e to the in phi. How do you embed them in three-dimensional rotations? Well, you just take j plus j. You want it lowest weight, so you want j equal plus n, m equal plus n. So it really points, it has the same. Okay. Pictures. I'm saying again the same thing, just I'm repeating it. Plane in space, it has a normal, or you can think of it as a two-form. But if you think of the plane in space-time, then you have the normal in space and the normal in time. So you have a two-form. And the map that gives from a classical plane a quantum plane, we did it in lecture 1. This is the map from a 4D plane, spatial plane, from classical to quantum. Okay? Okay. So all this was only for a plane. Now I have to do it for a polyhedron. But as you can see, there's everything at this point, because a polyhedron is not described in terms of edge lengths or positions of the vertices. It's purely described in terms of the planes that make the polyhedron. So the only thing that I really have to do is to say if a quantum polyhedron is an intertwiner between rotation representations, a quantum polyhedron in space-time, I just have to inject each one of them in space-time. And so it knows about the frame, and nothing changes. Every intertwiner becomes an intertwiner. It was closing, it still closes. What did I gain? Well, now I can boost it. Now I have a tetrahedron that lives on a plane, and I can ask, what happens if I boost the tetrahedron? Well, I'm going to boost the plane where the tetrahedron is. Does the volume change or contract? Well, the volume is defined as the volume on the plane. It's like the mass. The mass is defined as the energy in the rest frame. And, or better, no, it's really the invariant, the Lorentz invariant. And so the volume of the polyhedron is a Lorentz invariant. But the for normal, this one changes on the boost. So now I have many polyhedra, if you want many tetrahedra. I know how to boost one to the other, and I want the interaction of one into the other. Like for a particle, I have a particle, and then it goes into particles. But these particles that come out, they can be boosted with respect to the frame of the initial one. I want to do the same and write a vertex for this decay of a tetrahedron in 4 tetrahedra. And so I just have to take one of these, that goes into 4 of these. You see, I'm a bit more general. A certain number in, a certain number out. The example was 1 to 4. And I want it to be invariant. Carlo was writing it as, well, just project. I've written the projection a bit more explicitly. You can write the projection as an integral over the group. You say, well, if this and this are the two vectors, just integrate of all the boosts. This thing I was doing, I had to be careful. Boosts cannot send future pointing to past pointing. So I'm just boosting this way up to the null. So this makes it Lorentz invariant. Here there's the gamma that I was missing, and this one is the PRL model. Okay? There was somewhere here also. So this is projector over Lorentz. This is Y gamma. This is psi. Carlo did it for a general state. I'm doing it only for 4 quantum space coming from 1 quantum of space. And the evaluation of the identity, you don't see it because this was written in the holonomy representation. I'm already writing things in the spin network basis. Okay? And there are many ways of writing this same formula, many languages, many formalisms. If you go through the book of Carlo and Francesca, you find the map between all of them and which language, which mathematics is better for doing which calculation. But they are all the same theory. So the same picture that you have here, 1 tetrahedron into 4, written as a vertex. So there is one that I think that I should close with. That is this thing that is written here, the Barrett theorem, this thing that is important. Like, in the end, we just did Lorentz group representations. The only input that is gravitational is the dependence on gamma. So let's see if that dependence on gamma gives us back something that looks like gravity. Do these things subtract? Do this thing contain a GH bar? Is this, there's a way of saying it, that is, when you learn general relativity, you first learn differential geometry, and then you don't just do differential geometry. You also need the Einstein equation, so you also need, for instance, an action. And differential geometry doesn't give you the action, you have to give the structure, the mathematics, the degrees of freedom, and the action. And so if you want, all the Lorentz group things were the analog of differential geometry, but until I tell you how this map happens, how this going from 1 to 4 is like going from making a triangle out of 1 to 3, I haven't given you the amplitude. And so I'm asking a question about recovering general relativity. You cannot get general relativity for the full theory. We're doing quantum gravity is beyond general relativity. General relativity can arise only as a regime. To encode a regime is not a limit when you send constants somewhere. Constants, you measure them, they're dead. Regimes are, tell me what you prepare, tell me what's the experiment you're doing, tell me what's the state. There are some states that encode a regime where you go back to classical mechanics with small corrections. So if you prepare a state that is smooth and semi-classical with small fluctuations and you let it evolve, there's a question of does this evolve as if this was just general relativity. And here we're doing it in the small. Take a tetrahedron, a quantum tetrahedron, prepare it semi-classical, coherent, picked on a given shape, and look at the amplitude that this makes a transition to 4 tetrahedra that glued together nicely as the boundary of a 4 simplex. So to give them, I have to do this living speciale coherent states. I have to say the phase points in this way, in average, and then it has small fluctuations around that. So I first build the states, the coherent states, labeled by spins and normals, and then I compute the amplitude. So how do I compute the amplitude? I have to do this calculation. Given a state, compute the amplitude. Given the state, the coherent state for the boundary of a 4-dimensional object, for this length where there's 1 and 4, compute this amplitude in the regime where it behaves coherently. It behaves coherently when the spin is sufficiently large, so the dispersion is small compared to the average. Now, if you use the formula I was giving before, the calculation is difficult. You just have to do it. But if you go through the list of ways to reorganize or rewrite the formula, if you just use a lot of diagrammatics, you see that you can untie things and write things only as strands, lines, where you say, well, this phase, this triangle, is boosted into this other triangle, and there's a boost that is start from this triangle, go to the center, and then boost back to the other. And that's, if you want to learn these things, this is the exercise to do. Do it first 1-dimensional law, do Ponzano-Regge, 3D, and then you do this one. So once you write it in this way, then you still have to integrate over group elements. But now you have a parameter that is large. J is large because the state is semi-classical, and semi-classical has a J large. So you do this integral by looking at the saddle at large J of the log of all this. You evaluate it at the saddle plus corrections. And what you get out of that calculation, you get something that scales as e to the I j. All saddle point calculations give you dominating term e to the I large parameter phase. E to the I j. But here you see that the thing that dominates in this asymptotics is not just j alone. It's j together with a gamma. It's gamma j. Okay? Gamma j other things. Okay? Gamma j, you can write it as 8 pi g gamma j divided by 8 pi g gamma j. And so you divide and multiply, and you realize that this one here is the area. And the one that you divided in front is the ordinary 1/16 pi g of the action. And so somebody has suggested, well, Sophie was saying, well, there has to be a gamma and 1/gamma that cancel. That has to be the game. So you see, you get this gamma here, and once you see that there's a gamma j, then it's clear that you just have to multiply and divide by things with dimensions. That's the scale of area, and this is the thing that is there in the classical theory. And as you can see, there are other things. There's a boost, because you are going from one tetrahedron to another tetrahedron. And there's a sign, because you have to know if you have to time reverse or not. From going from here to here, you boost. But from here to here, there is no boost that does that. Or you can still say, well, I first boost a little bit, and then I time reverse. And so the time reverse is this epsilon. Epsilon is 1 from going from here to here, and -1 to go from here to here. And I give you a moment to think if you have comments. I know it was a lot. Go ahead. Yes.
You took the saddle point was taken, or the semi-classical limit is taken by taking the spin to large values.
J large. So up to here,
Yes.
everything is without approximation.
Yes.
And then here is where I say I have to integrate over G. And either you do it numerically, you really do the integral, or you say, well, I'm only interested in the value of the function or the dependence of the function on these parameters, the normals, when J is large. And so that's the saddle point.
Yes.
Approximation of an integral. If you want, there's no physics into it. There's really only like to compute an integral.
It seems to me that I can only do a semi-classical limit in the spin-based representation and never in the holonomic representation.
Oh, that's a very good point. So, that comes with the comment, and physics should be independent of the representation. No? Mm-hmm. So let me address that. We chose a boundary state that is semi-classical. I don't have to say the representation. It's semi-classical. Semi-classical means it's picked on all variables, intrinsic and extrinsic. And then I have to do a calculation. Now, it might be that doing the calculation is easier in some representation than in the other. That doesn't mean that one cannot decide, like, I really want to do it in the holonomy representation and not care that it's longer and more complicated. Then you still succeed.
But I want to know, of course it's complicated, but how do you do it? What is the thing you have to do for...
Yeah. So you still have to introduce a resolution of the identity, and then the holonomy representation is, I'm fixing J, but you might want to consider also superposition of a J. Okay. And in the end, the saddle point is always on these Lorentz transformations. And the picture that people often give is a picture that comes from, you start classical, you know that equations of motion come from a variation of the action equals 0. It's the action principle. But where does that rule, that law come from? It comes from a path integral. In the path integral, the integral is over e to the I s, and there are regimes where it's dominated by stationary points or saddle points. That is where the variation of the action is 0. And so that's how you get classical mechanics or classical equations of motion from quantum mechanics. And here we're going one step forward. That is, we don't even have the action yet. We want to get the action even before getting the equations of motion. There's a question should come up and it's not coming up. Why is that? Do you see? There's something I haven't discussed. Causality, good. More? It's DCC, yeah. What is DCC? Everybody hides it. Nobody writes cosine because you want to see e to the IS. Because in the patina, there's e to the I action, unless for some reason a cosine is the right thing that you are expecting because you are doing a calculation and you want cosine. And one says, well, it's e to the IS, apart from another term that is the complex conjugated. But if I really want the transition between, I prepare this, what's the probability I find that out? Then if that is the question, and I'm really saying this is not about what is the theory, is there an ambiguity. I'm saying we're doing a calculation of transition amplitude. You have to state what you are computing, and then the theory gives you an answer. If we ask different questions, the theory gives different answers. And so here I put arrows. But then in the calculation, you can see that the arrows never played any role. I don't know if you can see it, but there is nowhere written which one is future pointing, which one is past pointing. And I'm going to conclude with something that it's not out yet. It's in progress. It's with Chao Song, Monica, and Mauricio. I think it's stable enough that can fit us in here. That is, how do you encode causality? You have to tell if you can boost from one to the other, or you have to boost and time reverse. In the technical literature, these are called thin wedges and thick wedges because that's how people were doing the calculations. But it's clear that this is what the arrows tell you. You don't have an arrow of time, you just have relative things. Like when you do Lorentz group cannot send something future pointing to something past pointing. You have to add time reverse. You have to add the discrete part that you don't capture with the algebra. We want full Lorentz invariance, not Lorentz invariance only at the infinitesimal level. And so how do you do that? Well, it turns out that for some independent reason, the Wigner-D matrices, they do an average. If you are here and you boost here, they give you the Wigner-D matrix. But if you are here and you're doing time reverse and you're here, the Wigner-D matrix gives you the average between the two things because the Wigner-D matrix doesn't contain a notion of what is future pointing and what is past pointing. It turns out that this question had been asked and answered by Toller, and there's a unique decomposition of Wigner-D matrices into what I think is fair to call them Toller plus and Toller minus, the ones that boost this into this, and the ones that boost and time reverse. And so if now you know the data, you know that you want to go from here to here with the arrows all going up, it's clear that what you need is a transition amplitude that is a causal transition amplitude where you put a t plus if they're both future pointing or both past pointing, and a t minus if you need to do a time reverse and not just a boost. So now this is no approximation. This is what the theory tells you as the amplitude of that process. It's clear that if I wanted to average over the two, I would get back the answers I had before. And then there's a hard calculation one has to do to find what you get for a semi-classical state. And as you might expect, because of the question that we are asking, you get e to the I gravitational action. For this process, the gravitational action evaluated on this Regge transition, one Lorentzian polyhedron, one Lorentzian for simplex. It's exactly this form where you can recognize again GH bar, and the gamma is hidden here inside. And there is no complex conjugate because you're asking a causal question. And I think we still have some time for some more comments before we stop. Yes?
So we saw the operator algebra for this theory a couple days ago. I didn't quite have time to copy it down, but it was like had the areas and the fluxes, I think. And I want to bring up my question again earlier about the Peierls bracket.
Peierls bracket, yes. Formalism. You know that your physics is Lorentz invariant. You know that your physics has space-time symmetries. How do you work with them? You have to decide. Is it more practical to work in a formalism that doesn't make that symmetry manifest? Before speaking about this, let's step back and say, I'm doing quantum field theory on Minkowski space. I know that there's Poincare invariance. So how do I deal with it? Well, there are, as usual, two ways. One is, I work in a formalism where I make the symmetry not manifest. Be very careful when you say this. You're not saying you break the symmetry. You never broke, nothing breaks the symmetry. It's just that in your calculation, that symmetry is not manifest. It takes quite a few lines to show and check, but it's always there. So this is, at the classical level is you work with Poisson brackets. At the quantum level, you work with commutators equal time. And then the causal structure, all those things become not immediate to see. So if you work with PR brackets, you make all that structure, this Lorentz invariance and Poincare invariance, manifest at every single step of your calculation. You're essentially working only with 2-point functions in space-time. Now, why one would work with things that make symmetries not manifest? Why do the hard things? It seems that the other is easier. Well, first, don't forget that if you ask the question is independent of the formalism that you're using. We are only speaking about techniques for doing calculations. And you want your calculation maybe to be elegant or maybe to be such that it's easy to check steps. So if you have a symmetry that is manifest, it's easy to check. You look, the indices contract, and you're good. But it's not a theorem, but it's a rule or a fact that there is often a trade-off. You are making Lorentz or Poincare invariance manifest, but unitarity you have to check. Unitarity is easy to state. If you choose a foliation and you say it's unitary evolution from here to here, that is manifest at every single step. And so there you have this choice, like, do I have unitarity manifest, or at the classical level, Liouville evolution manifest, but covariance not, or the other way around? And particle physicists like to make everything manifestly Poincare invariant, and then you have to pay the price, like, is the theory unitary? Oh, come on, you define a theory that is unitary, but now you have to check every single step if you didn't introduce something that broke unitarity. And sometimes people say this, like, oh, the theory breaks unitarity at this level, at this point. Well, no, it's not it breaks unitarity. It's that the approximation scheme breaks unitarity, and as you don't have it manifest, you have to check it every time. So to go back to this, I would say it's the same story. Like, you could work canonically everywhere and answer that question canonically. You could work covariantly everywhere. The message that came up from this previous week of lectures on the big picture is it's good to use both, because you want to say how you prepare the system, how you measure the system, and so your detector has a frame. But then inside you want to sum over everything, so it's better to work with spin forms and make covariance manifest. And then you have to glue the two, and that was all this Y-gamma map. But don't forget that this is a formalism that makes the picture easy to read. But once you have stated clearly what is the question, what is the observable, the way you do the calculation doesn't affect the answer. That's only a technique for doing the calculation.
So I guess my question then is, like, when you actually write the algebra of the operators, can you just replace the brackets with the Peebles bracket?
Yeah.
Okay.
One more comment. Yes.
Can you explain this Stoller decomposition again?
Yes. The short answer. Chao's Song afternoon. We booked a Blackboard and we discuss it. One way is this thing I was saying. You can really decompose into boost up to a point and boost compose time reversal. The surprise is that the decomposition is unique. When you have something, you can always split it into pieces. There are many ideas. There were many ideas in the past of, well, we should split it, but is it a split done by hand? It turns out that there's a unique split that satisfies a list of group theoretical properties.
Because when we try to satisfy it for error of time, we will have to remove t minus term, right?
Yeah. Yes. Okay. Yes. Yes. You put either one or the other. And so you need a definition of this one independently of this one. The sum doesn't define the terms. Okay. One more comment? If not, we go. Thank you.